this right here is the distance between the point X and the point X naught. So if this is the point X naught right here, and that's the point X, so instead of writing it like this, you write it like that, and then this is written like that. Then this is the distance between those 2 points. Okay, so the between these two in the domain, and that is so the definition is that given epsilon there exists a delta such that that's less than delta implies that the value, this function value, is arbitrarily close to L, okay, within epsilon. Okay, so that's the technical definition. We probably not gonna, I think I'm not gonna really make you do that. But there's a few things to remember when you're calculating limits. Okay, and so when the limit exists, or when does the limit exist? Okay, so you can tell, usually you can, so you can try plugging in the point and see if that works, and if it does, then, then probably the limit exists and that's what the value is going to be. Okay, except in like weird cases, which you would be able to identify. Okay, so you plug in the value, that's one thing. You might have to manipulate it first. Okay, then plug in the value. Okay. Okay, so you might have to do some manipulation first and then plug in your point. Okay, but if you're able to do that and the point doesn't cause trouble, then that's probably going to work. That's probably good. And then in the end, though, you might have to resort to the definition to find the value. Okay, so you might have to resort to that. Okay, now when the limit doesn't exist, so that would be the D and E answer. The way that you do that one is what typically happens there is you get different values on different paths. And that's an indication. If that happens, then the limit doesn't exist. Okay, but if you take like a couple of different paths and you get the same limit on 2 different paths, it doesn't necessarily mean that the limit exists, though. So this only works when the limit doesn't exist. You take on 2 different paths and you get different values, then the limit doesn't exist. Okay, and I'll show you. I'll try to show you some of each of these examples here. And the definition of continuous means that the limit is equal to the value at the point. So that's just like before. Okay, so let's go ahead and take a look at some limits. So we're looking at number 1, find the limit if it exists of as x goes to 0, 0. So you notice that the problem is that there's zeros in the denominator, right? When you plug in this point, you get 0 in the denominator. Okay, so what to do here?
You can just differentiate both of them. Then input.
No, L'Hopital's rule doesn't work. So.
Oh, really?
L'Hopital's rule doesn't work here. That's not one of the options. But it sounds like maybe there's some modified. I've never heard of L'Hopital's rule working, but maybe there's some kind of a modified version. I may have to look that up. But it doesn't work here. This one's kind of hard to see if you've never seen this kind of stuff before. But I guess what to look for, let me see. If you approach this problem, let me just kind of try to analyze what I see here. Okay, so I have the second power here, right, of y. So these powers are the same, right? And then, but these powers are different. Okay, but that power is larger than that power. Okay, so those are some of the stuff that I see. So one thing that you can try is these two different paths. So let's suppose you want to go along x equals 0. And let me try to draw a picture of what's going on here, okay? So here's the point 0, 0, right? We are approaching, well, basically looking at what happens as you approach that point, okay? Kind of from all different directions is what's happening. You're approaching this 0, 0 point, which is right there, from all different directions. Okay, that's what that limit is. So approaching it along x equals 0, that would be approaching it along here, but also, you know, this way as well. Okay, so you're approaching it this way. So this is more like the limits that you have before. Okay, so when you set x equals to 0, then so basically x equals 0. So make these x's 0. This part's gone, and it becomes a limit as y goes to 0 of negative 38y squared over 19y squared. Okay, and that's going to be the y squareds cancel, and it's going to be negative 2. Just reduce to negative 2. Okay. Then we go along x equals 0. Okay, and then so that's coming along here. Okay, so this path's along there. Okay, so here you set x equal to 0. No, I'm sorry. I meant y equals. Oh man, I totally messed this up. This is bad. This is wrong. Okay, let me try again. So the blue one, x equals 0 is actually here. Okay, that's x equals 0. And then y equals 0 is here. Dang, I don't know what to do. This is like the first time I ever made a mistake. Probably because I'm recording these live and I'm nervous. Yeah, okay. So limit as x goes to 0. No. Yeah, so this is going to be, if y's are all 0, then those are all gone. And you have x to the 4th over x squared. And what's that limit going to be?
X squared.
Yes. And it's going to be 0, right? Okay, so these are different values, which means that the limit does not exist. So just put D and E in for the answer. And Webassign says, yeah, that doesn't exist. Okay, so that's an example. Now, just because if I had gotten the same limit for both of these, then it doesn't mean that the limit exists. So, okay, so that's an example of this right here, how to show that the limit doesn't exist. You get different values along different paths. Okay, now the next problem, we have this limit here, and let's see, things that you can note is that these are both like to the first power, right? And if you take this ignore the y squared for now. If you take that, you get x to the first power, well, the absolute value of that, right? And then the y squared is also the same. So these are kind of, so you have an x and a y there, and then you got x squared plus y squared down here. Okay, so this has a good chance of, this one, they're evener. So this one we had the x to the fourth up here, and this threw things up, and these were the same, which made it so that you'd get different values. Okay, but this one, everything's the same, basically. And they're kind of worked in together. And I suppose it's really hard to see this, but x is going to be less than or equal to x squared plus y squared in absolute value. Right? And then y also is going to be less than or equal to the square root of x squared plus y squared. So that means that if we take this expression right here, that's going to be equal to, that's going to be less than or equal to the square root of x squared plus y squared times the square root of x squared plus y squared over the square root of x squared plus y squared. And then those are going to cancel, and you're going to get the square root of x squared plus y squared. And then if you take the limit as xy goes to 0 of the square root of x squared plus y squared, you get 0. Because when you plug it in, you're going to get 0. Okay, so so the answer here is going to be 0. So this is an example of just doing some manipulation first, but it's also comparing. Okay, so this is sort of using the limit definition. Okay, this is using the limit definition. And so maybe what I should say is, instead of using the limit definition, another option would be, I don't know, I would say something like some sort of a squeeze, or some kind of a comparison to another function with another limit. That's sort of what we did there. Okay, but you can also pivot and you can use this argument here for doing the limit. Okay. So let's go on to number 3. The limit as x, y approaches 0, 0 of all this. And what do you think we should do here? I'll give you a hint. You're going to multiply by another fancy form of 1. And I'm sure that's going to work. So what would we multiply by?
Is it the bottom part? No.
The bottom part?
Yeah.
This part here?
Mm-hmm. And then plus it. Are we doing the, what do we call it?
The conjugate.
The conjugate.
Yeah, plus 9. Yeah, I don't know I think that's called the conjugate. I guess you could call it the conjugate there. I don't know for sure, but let's just call it that. Okay, so then what happens is the denominator becomes x squared plus y squared plus 81 minus 81, right? And the numerator is x squared plus y squared times all this plus 9. And then this is the fun part, the 81s cancel. And then once all those 81s are gone, it's just this and this, and they cancel. And then you can just plug in the value, right? So plug zeros in there, you get the square root of 81, which is 9. So you get 18.
Wow.
Okay, number 4. Here we have 3 different values for number 4. You have x, y, and z now. So you're coming in 3 space to the origin, 0, 0, 0. Okay, so what? Let's see. Let's look at, we got z to the 4th here. I've got a z squared there. We have x squared there and a y squared there.
Can we simplify it? No. No, we can't.
Doesn't look like it because this denominator has got just 1 of each term here. So that really doesn't factor in anything. And then this is just weird too. This one has, these ones have x's, but this one doesn't. These have z's, but that doesn't. These have y's, but that doesn't. So boo. Boo, boo, boo. This is, okay, so now what you can do here, and maybe this is hard to see, but see this z to the 4th right there? If every term had z to the 4th, that would be really fun, right? If this was something, if this is like z to the 4th, and this was 9z to the 4th, and this was 5z to the 4th, and these were z to the 4th, then we'd be able to find the limit, right? So what you're going to do is you're going to say, okay, let's go in along x equals z squared and y equals z squared. Okay, so that's certainly a path that's going to take us to the origin, because when z goes to 0, x is going to go to 0. Okay, and y, so is y, if we make these 2 conditions right here. Okay, so if we do that, so basically we're plugging in z squared for, we're plugging in z squared for x and for y. So this is z to the 4th. This is 9 z to the 4th. And this is, so x is z squared, so that's 5z to the 4th. And then these are also z to the 4th as well. Okay, so the numerator we have 15z to the 4th over 3z to the 4th, and that the z to the 4th is going to cancel, and we're just get a 5 as the limit, right? Okay, but again, this is along a certain path. So really, maybe, so what's my strategy here? Is it to find the limit, or to maybe show that the limit doesn't exist? So let's take another path. What's like an easier path? Maybe x is 0 and y is 0, right? That would be an easier path, right? So that would be the limit as z goes to 0. And what would you have in the numerator? So immediately, everywhere they see x's and y's, you make them zeros, right? That's going to be a 0. And that's going to be a 0 also. And that's going to be a 0 also. Hey, how do you like 0 plus 0 plus 0? Isn't that great? 0 plus 0 is 0. Well, if the denominator is that way, then we're not good. But okay, so 0, 0. But then this is z to the 4th. Okay, so you have the limit as z goes to 0 of 0 over z to the 4th, which is just going to be 0, right? Because that's always 0. So okay, so now what does this mean?
The limit does not exist.
Yes, the limit does not exist. Okay, so that limit does not exist. Okay, number 5. Number 5, we're supposed to find the composition of these two functions, this right here, and then we're supposed to say whether where it's continuous. We're supposed to find where it's continuous. Okay. Okay. So it's this function of this one. So that means we take. So it's going to be g of all this. And since the t has been replaced with this, then we replace these t's with that. And I don't think we can simplify it any further than that. So let's go ahead and put that in as an answer and see what Webassign says. Okay, and then the next question is, where is it continuous? And what are potential problems? We could potentially have a 0 in the denominator, right? But is this ever going to be 0?
No, it will never be 0.
Is that sad or is that happy? I don't know. Well, I don't know what to say. I guess that's happy, right? Because the denominator is never 0. Okay, so this one right here. So that's not a problem at all. Okay, the only problem is right here. If you're taking the log of a number, it has to be positive, right? That means that 5 minus xy over, so this right here, has to be greater than 0. Okay, now the denominator is always positive, so this is only going to happen if only if 5 minus xy is greater than 0. But you can take the xy over here, and then you can flip it around, so it's like that. Okay. So xy less than 5, I think, is what you're going to look for. Yeah, I see that there. Yep. Okay, great. So that's number 5. Number 6. Oh, where is this one going to be continuous? And it appears that the numerator looks okay. So what about the denominator? What do you need the denominator to be?
Nine.
Yeah, you can't. Yeah, it can't be that 9. It can't be 0. Okay, so x squared plus y squared not equal to 9 is what you're going to need. So it's going to be everywhere except that. Okay, just like that. And then number 7, where is this function continuous? So here it's defined this way when you're not 0. It's not 0, 0. But then at 0, it's defined to be 0. Okay, so I guess the question now is, what's this limit going to be? Okay, so if this limit is 0, then it's continuous. If this limit is not 0, or If the limit doesn't exist, then it's not continuous. So how do we, so what do you guys think? What should we do here?
Try to prove that it won't be 0 or something like that.
Yeah, try to show it's not 0. Well, maybe we should try to figure out what the limit is, or show that it doesn't exist.
I think that we
So
should
can
show
you-
that it doesn't exist.
What's that?
I think we should show that it doesn't exist.
Okay, so if you're gonna do that, then we have to choose paths.
Oh, dang.
So-
Yeah, that's fine.
Does anybody have a suggestion for our first path?
Either way, Brother Hurst, don't you get 0 on the top, even if you choose X is 0 or Y is 0?
Yep, those two paths give you 0, right?
Right.
If you choose
You
x
always
equals
get X
0,
on
then you're
top.
taking. Yeah, so if you choose x equals 0, then you're going to get 0 on the top, and then you're going to have over y squared. That's going to be 0, right?
Right.
Yeah, and then if you choose y equals 0, then it's also going to be 0. So is there another path that we can choose? So that's not going to show that this is not continuous, unfortunately. Is there another path?
X is equal to 1 or Y is equal to 1.
You can't do that. That doesn't. Okay, so you can't just choose. Those don't go to 0. So if you're going x equals 1, that's right here. You're never going to get to that point there if you're choosing x equals 1. X equals line would be a vertical line right here. And you can never get to 0 from this path.
What about factorizing? No.
What's that?
Factorizing it. The bottom part.
There's a path that gives you a different value. I'll give you that hint. Because you can tell because all of these are the same power. Well, collectively. So so this is a 1, that's a 1. That's a 2. These are 1s. Okay, so these add up to 2. That's 2. These add up to 2, and that's 2. All 2s. That's a hint that that different paths are going to do different things. But this path going through along x equals 0 gives you 0, and this path gives you 0. But we come in a different direction. Okay, so what is this path? It goes through the 0. What's this path? What's this equation? What is the equation of a line, right? It's y equals.
X.
Yeah, so you're going to go along that path, okay? Okay, and that's going to give you, okay, so you're making y is x. So that means you're going to have a limit as x goes to 0. And the numerator is going to be what? If we substitute this y for an x, then we'll have x times x, right? We'll have x squared.
Square.
This is still an x squared. This becomes x squared, and that becomes another x squared. Okay, so this is going to be 1/3, right? Okay, so these are not equal, so that means that doesn't exist. That means that continuous everywhere. Except at 0, 0. Okay, because this is not going to ever be 0. Well, yeah, this is never going to be 0. This is always going to be greater than or equal to 0. And the only way it's 0 is if all of these are 0. If x and y are both 0. Okay? Because if you try to solve for this, then the only solution is 0, 0. X equals 0 and y equals 0. Can you guys see that? That's kind of hard to see. But if either of these is negative, then this middle term can be negative, right? If x or y is negative, then the middle term is negative. But it's always going to be, the middle term is always going to be less than or equal to, in magnitude, less than or equal to either x squared or y squared. So, but anyways, just the bottom line. Continuous everywhere except 0, 0. So, looks like the fourth answer is the right answer. Great. So that's limits and continuity 14.2. Once again, when the limit exists, you can plug in the point, manipulate first, resort to the definition, or use comparison test, or some kind of comparison argument. And to show the limit doesn't exist, then you go to different, you show there's different values on different paths. Okay, and this is also tricky because a lot of times you'll have two different paths that gives you the same value, but that doesn't necessarily mean the limit exists. So you have to do one of these things to show the limit exists. Okay, great.